Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing, the most shocking developments that are going to touch our lives and change the way we view the universe. And in this hour, we're going to explore the universe with astronomer Ken Croswell. We're going to talk about the sensational comments being made by billionaire Elon Musk to create a city on Mars. This is something ripped off the pages of a science fiction novel being proposed by one of the nation's leading billionaires pushing the space program. And then we'll talk about sending the first starship to the nearby stars. Stephen Hawking, my colleague, stunned the world by announcing that a new generation of starships could be in the making. Not something from a Hollywood movie lot like the Enterprise, but starships perhaps traveling at 20% the speed of light, looking like a postage stamp that is sending chips by the thousands to the nearby stars. And once again, with us today to talk about these things is astronomer Ken Croswell. And one day, perhaps, we'll try to get Elon Musk on the airwaves as well. His plan is incredible. In 2 years' time, he wants to send an unmanned probe to Mars. And just think about that. Privately financed, an individual being able to send his own personal spaceship to the red planet in 2 years. And then by 2024, perhaps 10 years before NASA itself, he wants to send the first manned mission to the red planet. And then the ultimate goal is to send 1,000 spaceships with 100 colonists each, creating the first city on Mars. All this, of course, is incredible, unless, of course, it was mentioned by a billionaire who has a proven track record of exploring the universe. You know, when I was a kid, looking up at the stars, looking at the red planet, it seemed incredible that one day we might be able to live there. In fact, another young kid by the name of Carl Sagan used to read science fiction novels as well, including the John Carter of Mars series. Well, Carl Sagan went on to become a famous astronomer. But when he was a child, he dreamed of chasing the beautiful Princess Dejah Thoris on the sands of Mars. He dreamed about walking on the red planet. Well, unfortunately, he passed away before that dream could be true, but hey, who knows? In 20 years' time, that's the time frame of NASA. That's more or less the time frame being laid out by Elon Musk. In 20 years' time, the first manned mission to Mars may become possible. And within that time frame, perhaps within the next 50 years, we might send the first starship to Proxima Centauri. Proxima Centauri is a little more than 4 light years from the planet Earth, making it the nearest star to the Earth. And Stephen Hawking, as I mentioned, wants to send computer chips, tiny computer chips the size of a postage stamp, on laser beams that are hurtling at 20% the speed of light. So we're talking about a new form of interstellar travel. Forget about the Enterprise. It simply costs too much money and would take too long to send the Enterprise to the stars. But a postage stamp full of computers, cameras, full of sensors that could broadcast gorgeous photographs back to the planet Earth, that's something that is definitely possible. There is, of course, a bottleneck there. The bottleneck is you have to have a bank of laser beams to the tune of 800 megawatts. That is equivalent to 800 nuclear power plants. 800 gigawatts, 800 billion watts of power, equivalent to the energy output of 800 nuclear power plants. All that energy concentrated into a laser beam that then illuminates a parachute. And it pushes the parachute to 20% the speed of light. At 20% the speed of light, yes, you can reach the nearby stars in about 20 years' time. So the dream the dream of reaching the nearby stars is not so far-fetched. And so things that we once considered to be just out of the question, like building a city on Mars or sending the first rocket ship to the nearby stars, things like that are now within the realm of possibility. Now, of course, this is not going to happen anytime soon. We're talking about billions of dollars. In fact, 10 billion is the number that Elon Musk himself floated for the first manned mission to the red planet. And with us today, once again, is Ken Croswell, astronomer at Berkeley, who will talk to us about the science of what it would be like to walk on the surface of the red planet. Would it be like walking on the moon? No, totally different. But would it be like being a pioneer of some sort to walk on the surface of Mars? Well, we'll find out more after we take a short commercial break. Once again, our special guest today is astronomer Ken Croswell of Berkeley, author of The Alchemy of the Heavens, and you are listening to Science Fantastic with Michio Kaku. And in a few minutes after the commercial break, we're going to explore the red planet. Think about that, sending the first colonists to the red planet by 2024. That's the dream of billionaire Elon Musk.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to explore the universe with our favorite astronomer, Ken Croswell of Berkeley, author of a number of great books, including The Alchemy of the Heavens, Searching for Meaning in the Milky Way. And we're going to talk about, well, everything happening in the universe. First of all, you probably heard that Elon Musk, the billionaire behind SpaceX, PayPal, and Tesla Motors, has made this stunning announcement that has shocked the scientific world, catching many people off guard. He says, yes, it's on to Mars. He envisions a time when we'll have 1,000 spaceships with 100 colonists in each one, creating a city on the red planet. Is this hokum or is this real, given the fact that we now have a billionaire, the man behind SpaceX, the man who has already revolutionized space travel by introducing the reusable booster rocket? How seriously should we take his comments? And we'll also talk about Alpha Centauri and Proxima Centauri. Did you know that we now know there is an Earth-like planet that's literally a hop, skip, and a jump from the planet Earth, 4 light years from the Earth? The nearest star to the Earth, Proxima Centauri, has an Earth-like planet going around it. Who would have thought? And with us today, once again, to talk about all these developments in the universe is our favorite astronomer, Ken Croswell. So, Ken, first of all, what was your initial reaction hearing the fact that a billionaire is now proposing that we become a multi-planet species, that we go onto Mars and perhaps set up a Mars colony? What was your first gut reaction to that?
Well, if we could do it, I think it's a great thing because it obviously diversifies the human race. Instead of being on just one planet, we'll be on 2 planets and maybe eventually more than 2 planets. And so if something terrible goes wrong, terribly wrong goes on with the Earth, at least some human beings will survive. Having said that, Mars is a very difficult planet to live on, even though it is the best planet in the solar system, aside from the Earth. It's a very hostile planet. It's very cold, very thin atmosphere. There's essentially no oxygen to breathe. It's a hostile place, much more hostile than Antarctica in many ways. And so it's going to be an enormous challenge. But I certainly don't want to stand in the way of anyone who's got the vision to try to colonize Mars, because it would be a wonderful thing if we could achieve it.
And speaking about colonizing Mars, he even gave a timetable. In 2 years' time, he wants to modify the Falcon rocket to send an unmanned probe to Mars. Think about that. Here is a private individual, not a nation state, a private individual who will send an unmanned package to the red planet in just 2 years. And then in 2024, he's going to beat NASA perhaps beat NASA by 10 years, in fact, by sending the first manned mission to the red planet. Well, before we get all hyped up and breathless thinking about this, let's talk about the reality. You probably saw the movie The Martian. And so tell us a little bit about how cold it is on Mars, and what would it be like to walk on the surface of Mars given the fact that the slightest tear in your spacesuit could kill you. So what would it be like to walk on the surface of Mars?
Well, Mars is basically a dry desert. It's it probably look a lot like Arizona, depending on exactly where you would set down, and it has a very thin atmosphere. So you would definitely need a spacesuit. This is not a place you could just walk around without a spacesuit. You definitely need a spacesuit. It's cold usually, although during the warmest times of the year and at the best places on Mars, it can get up to 70 or 80 degrees Fahrenheit. The problem is at night it then plunges way, way, way below zero. So it's a very hostile environment, very cold. There are global dust storms. You don't have to worry about rainstorms or snowstorms, but you do have to worry about these dust storms that occur every now and then that actually blot out the entire planet. In fact, when the very first orbiting spacecraft arrived at Mars, this was Mariner 9, which was an American mission in the early 1970s, the spacecraft had the bad luck of arriving when the planet was surrounded in dust and the spacecraft couldn't see anything. Fortunately, the spacecraft lasted long enough so that eventually the dust storm died down, and it was able to make a lot of major discoveries, including volcanoes on Mars and dried-up riverbeds on Mars. So we do think that in the past, billions of years ago, Mars was a better place because we do see evidence of riverbeds in the oldest parts of Mars. But today, Mars is a very hostile place, just like the Moon, but much harder to reach than the Moon. So again, I definitely don't want to stand in the way of anybody who's got the vision and the money to attempt to explore Mars. But it will be a great challenge. But I'm sure he knows this. He knows this is a challenge, but I think that's why he's doing it.
Right. And let's talk a bit about walking on the surface of Mars. First of all, gravity. Usually in science fiction movies, the gravity on these alien worlds is exactly the same as the gravity found in a Hollywood movie set. In other words, 1G. But what would the gravity be like on Mars? And then also, what about radiation and micrometeorites? Some people say that we should live underground on Mars simply because the surface of Mars could be bathed by radiation and micrometeorites. So what would it be like to walk on Mars?
Well, the gravity on Mars is less on the surface than it is on the surface of the Earth. That's because Mars has less mass than the Earth. It's only about 10% the mass of the Earth. But it has more surface gravity than the Moon does. On the Moon, the surface gravity is 1/6 that of the Earth. On Mars, it's 38% the surface gravity of the Earth. So you would presumably feel lighter on Mars than you do here on Earth, but I would imagine eventually you would get used to that. You might have a little bit of a problem in that, it's gravity on Earth that helps to keep our bones and muscles strong. I mean, if you were to live in a zero gravity environment, your muscles and bones would deteriorate. So there is a risk, it seems to me, that even at Martian gravity levels, you might want to engage in exercise just to keep your body fit as it is here on Earth. And as far as your other question was concerning the environment of Mars is, of course, very hostile. You would always need to wear a spacesuit. There is ultraviolet radiation from the sun because Mars has essentially no ozone layer, unlike the Earth. It's, of course, the Earth's ozone layer that protects us from the worst ultraviolet radiation from the sun. Mars has no ozone layer because it has almost no oxygen in its atmosphere. So that's going to be a problem. And as you mentioned also, micrometeorites. Mars does have an atmosphere, so that should shield the surface somewhat from meteorites, but not nearly. It's not nearly as thick an atmosphere as the Earth has. So that could be another problem. So these are all going to be challenges. But again, I think anyone who's seriously considering moving to Mars will know these things in advance.
Okay, and speaking about moving to Mars, many of the scientists who've looked at it say that we can reduce costs by, quote, living off the land. Think of the early pioneers. They didn't bring with them all the luggage and water and food from the old world. No, they shot rabbits, they raised crops and so on and so forth, and lived off the land. But Mars is different. Can you live off the land on Mars? For example, crops. What would it take to raise crops on Mars?
Well, I'm pretty sure there are no rabbits on Mars right now. But growing crops, it seems to me, should be possible. We know that the surface of Mars, the elements in that surface, are rather similar to those in the surface of the Earth. There's definitely ice on Mars beneath the surface at many of the latitudes, so you could water the crops. I don't think growing crops would be a big problem. And in fact, in some ways, the crops might be more nutritious because the surface of Mars has more magnesium and iron than does the surface of the Earth. So you never know. Someday, in the far future, we may be importing food from Mars to Earth, and it'll be advertised as especially high in iron and magnesium because it was grown on Mars. You may look for that at Whole Foods someday in the future.
Okay, well, for those of you who saw the movie The Martian, some of you perhaps were grossed out by the fact that Matt Damon didn't have fertilizer to create the first generation of crops to eat. So he used his own waste products as fertilizer. A lot of people were grossed out by that scene. However, the question is, well, does Mars have any fertilizer at all? What about soil? What about the topsoil of Mars?
Well, there's not much organic material there. I mean, every now and then, a meteorite falls and might give the planet some organic material, but that might be something we'll need to import. Maybe that's the one thing that Earth can supply to the rest of the universe, namely poop, to fertilize the soil of other planets.
Okay, well, let's take a short commercial break, and after that, we're going to continue our discussion of going to Mars and then going to the stars. Perhaps one day we'll go to Proxima Centauri, an Earth-like planet orbiting that star.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about going to the red planet. You probably heard that billionaire Elon Musk laid out the most elaborate time frame by which to create not just a colony on Mars. We're way beyond that. He wants to create a city on Mars with 1 million inhabitants. Think about that. A new home in outer space. Is this just outlandish science fiction, or is there some truth to what he says? Because after all, Elon Musk is a physicist. With us today is astronomer Ken Croswell, author of a number of great books, including The Alchemy of the Heavens, Magnificent Mars, Magnificent Universe, and he's going to talk to us today about Mars and also the nearby stars. Will we one day send a starship to the nearest star in the heavens? Well, Ken, we were talking about growing crops on Mars. Some people think that one day we'll terraform Mars, that is, turn Mars into a Garden of Eden, by first of all heating up the planet, maybe 6 degrees or so that the polar ice caps begin to melt, which releases more water vapor and organic and also chemicals in the atmosphere that are greenhouse gases, which would accelerate the greenhouse effect. In other words, creating an artificial greenhouse effect if you could jumpstart it by raising the planet's temperature by about 6 degrees. So what are your thoughts? You think that one day, not anytime soon, but maybe in 100 years or so, we might contemplate the idea of perhaps melting the polar ice caps or inducing an artificial greenhouse effect?
Well, you're right. That's not something that's going to happen in our lifetimes, but it could conceivably happen centuries from now because, as you point out, water vapor is a greenhouse gas, and the Martian atmosphere already contains another greenhouse gas, namely carbon dioxide, which makes up 95% of the Martian atmosphere. And another greenhouse gas, if we could somehow get a supply of it is methane. That's a very potent greenhouse gas. And, of course, Mars needs a much stronger greenhouse effect than the Earth has because it's about 50% farther from the sun than the Earth has. And, keep in mind, even the Earth has a substantial greenhouse effect. If it weren't for the greenhouse effect here on Earth, Earth would be 60 degrees Fahrenheit cooler than it actually is, and it would be an ice-covered planet, probably quite hostile to life. So even we, at a distance of 93 million miles from the sun, we need a greenhouse effect. And unfortunately, the Martian atmosphere right now is so thin that it raises the temperature. The greenhouse effect raises the temperature only about 10 degrees Fahrenheit. So we need to substantially boost that greenhouse effect on Mars if it's ever going to be a pleasant place to live. And I don't know if that's possible. I really don't know. But it will obviously be a great challenge, and it's not, as you point out, it's not something that's going to happen in our lifetimes.
Well, Elon Musk, of course, always has aces in the hole, and this time is hydrogen warheads. He wants to nuke Mars. Think about that. We have the polar ice caps, which contain plenty of dry ice and ordinary water ice, but you have to have some way to melt it so that water will one day again flow through the old ancient river channels of Mars. And he wants air bursts. He wants to detonate hydrogen bombs over the polar ice caps so that, of course, you don't want to disturb the geology of the planet. Air bursts to begin the process of melting the ice caps so that liquid water flows on the surface of Mars. Well, what are your thoughts? Everybody has an opinion upon this. What are your thoughts about nuking Mars? Is it just outlandish, or is it feasible?
Well, I would look for a more peaceful way to achieve the same ends. I think, there surely are better ways to melt the ice on Mars than to nuke the planet. Who knows what the consequences would be? I mean, if the goal, of course, is to make Mars habitable, I don't see how having a bunch of radioactive material on Mars is going to help in that regard. I would look for some way to maybe deflect sunlight toward the poles of Mars. That might be one way to melt the polar caps. And I'm sure many other people could come up with other ideas as well. But no, I don't think it's a good idea to nuke Mars.
Okay, and some other ideas have been proposed. One of them is to deflect a comet, because after all, comets are mainly made out of ice, water ice. So if you could nudge a comet and have it then orbit Mars so that it slowly disintegrates, then you can inject large amounts of water vapor into Mars, and of course water vapor is a greenhouse gas. And you also mentioned solar satellites that could beam light energy from the sun onto the polar ice caps. So what are your thoughts? Is this feasible? Is it within the laws of physics that we might be able to deflect a comet? Or, as you mentioned, perhaps create an array of solar satellites to beam solar energy down to the polar ice caps?
Well, certainly solar satellites make a lot of sense. That would definitely warm up the planet. And as far as steering a comet to disintegrate into Mars, that will be a more challenging task. But it's conceivable we could do something like that.
Okay. So, Ken, let's take a short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. After the break, we're going to go to the stars. That's right. Physicists are now contemplating reaching the stars. And we'll talk about that in the next segment of Science Fantastic. Once again, give us a call. The hotline number is 866-323-2129. All we ask is that you leave your name, call letters of the radio station you're listening to, and the city you're calling from, and perhaps you can get on over 100 radio stations that carry Science Fantastic. So stay tuned, because in the next segment, we leave Mars and go to the stars with Ken Croswell, author of the book, The Alchemy of the Heavens. So stay tuned.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about exploring the universe with astronomer Ken Croswell. We started off by talking about Mars, the fact that billionaire Elon Musk laid out perhaps the most ambitious timetable ever, not just to reach Mars, but to build a city on Mars. Think about this, a million inhabitants in a city on Mars. Now we're going to go even beyond the red planet. We're going to go to the nearby stars. You know, when I was a kid reading about science fiction, the whole idea that one day we could reach Alpha Centauri, the nearest star, that seemed so far-fetched. But now, perhaps it's not such a far-fetched idea, because apparently there is an Earth-like planet orbiting that star. Once again, with us today is astronomer Ken Croswell, author of the book, The Alchemy of the Heavens. So, Ken, tell us a little bit about Proxima Centauri and the discovery that is shaking the world of astronomy of a planet, an Earth-like planet orbiting that star.
Yes, this is definitely one of the biggest astronomical discoveries of the year. Proxima Centauri is the nearest individual star to our solar system. It's a star quite different from the sun. It's a very feeble star. It's a red dwarf star. It emits much less light than the sun. In fact, it's so feeble that even though it is the nearest individual star to the sun, it was only discovered in 1915. Its star is not visible to the naked eye. You need a telescope to see it. And it's actually part of a larger star system called Alpha Centauri. Now, Alpha Centauri is visible to the naked eye, and altogether the Alpha Centauri system contains 3 stars. One is yellow, very similar to the sun. The other is orange, and it's a bit fainter than the sun, a bit less luminous than the sun. And then there's Proxima Centauri, so dim that you cannot see it with the naked eye, even though it's just 4.24 light years away. And the big news is that there is a planet, similar in mass to the Earth, going around this star every 11.2 days and located about 4.5 million miles from the star. Now, if you had a planet that close to the sun, it would be a terrible place to live because it would be really, really hot. I mean, that's closer to the sun than Mercury is. And Mercury, of course, is a very hostile planet. But because Proxima Centauri emits so little light, it turns out that this newfound planet around Proxima Centauri is actually in the habitable zone of the star. In other words, potentially, the temperature on this planet could be just right to have liquid water and some form of life if the planet has a decent atmosphere. So this is a very exciting discovery, and of course we would love to explore that planet close up by sending a spacecraft there.
Okay, let's take another short commercial break. Once again, you are listening to Science Fantastic.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is astronomer Ken Croswell, author of the book Alchemy of the Heavens and a number of other great books. And we're talking about, well, going to the stars. We talked about the fact that there is a planet, an Earth-like planet, orbiting the nearest star in the heavens, Proxima Centauri, and Stephen Hawking. Stephen Hawking, my colleague, recently announced that he wants to send starships to the nearby stars. Now, not like the Enterprise, not like something from Star Wars. We're talking about something the size of a postage stamp, shot by laser beams in a parachute that would then reach 20% of the speed of light, the ultimate velocity in the universe, reaching Alpha Centauri in perhaps 20 years. So, Ken, what are your thoughts, first of all, about whether or not that's an outlandish scheme or whether there's some truth to the idea that we can send tiny chips to the nearby stars?
I like the idea because in order to reach even the nearest star system, Alpha Centauri, we're going to have to go really fast. Otherwise, it's going to take forever. And, of course, I would love to see this Proxima Centauri planet, which is similar in mass to the Earth, close up during my lifetime. And so that means you have to go really, really fast. The problem is, to go really, really fast, you need a lot of energy with a normal-sized spaceship because the kinetic energy is 1/2 mv squared, where m is the mass and v is the velocity. So if you can decrease the mass of the spaceship dramatically to something that's just less than an ounce, say, then you don't need nearly as much energy And so it becomes much more feasible. So I do like the idea in principle. Whether it's going to work or not, I have no idea. And frankly, I don't think anyone knows for sure if it'll work. But it's certainly, it's, you know, any of these suggestions that will get us to Alpha Centauri fast, you know, I encourage. So I'm all for, you know, wanting to see Proxima Centauri's planet close up. Because think of our own solar system. How little we knew of the planets in our own solar system before spacecraft flew past them. We were talking about Mars a few minutes ago. How little we knew about Mars. I mean, some people thought it had intelligent life. Some people thought it had plants. In fact, it's got neither. Instead, it's got lots of craters, but also riverbeds and volcanoes. And we learned all that through spacecraft. And likewise, this Proxima Centauri planet is very exciting. And in order to learn more about it, to learn a lot about it, we're going to need to send a spacecraft past it.
Now, leaving the stars, let's go beyond the Milky Way galaxy to other galaxies in outer space. Recently, there was a discovery of a dark galaxy, which freaked people out. It's a galaxy with very few stars in it, but has dark matter, invisible matter that makes up an entire galaxy. Could you explain how upsetting this is to people who think of galaxies as being beautiful pinwheels in outer space?
Well, this is a whole new breed of galaxies. It was identified in large numbers just a couple years ago. These are called ultra-diffuse galaxies, and they are as large as the Milky Way, but they emit as little light as a dwarf galaxy. Now, our galaxy is a giant. It's much bigger than most other galaxies. A very brilliant galaxy, and it's a very big galaxy. And these ultra-diffuse galaxies are also very big, but they're very dim. And so it's been a real mystery as to how these things form. But we do know that they have lots of dark matter because many of them reside in galaxy clusters. And if they didn't have a lot of gravity to hold themselves together, they'd get torn apart by the other galaxies in the cluster. So even early on, we knew that. And more recently, astronomers used the Keck telescope to measure the mass of one of the largest of these galaxies, whose name is Dragonfly 44. And they discovered that despite the dimness of this galaxy, it weighs about as much as the Milky Way, namely about 1 trillion times the mass of the Sun. And so that tells us that even though it's emitting very little light, and thus has very few stars, it's got an enormous amount of dark matter. So this galaxy consists of over 99.9% dark matter. So it's a whole new breed of galaxy. We don't understand how these things formed. There are various theories out there, but it's a whole new phenomenon for astronomers to study, and it's wonderful.
Does this mean that all the astronomy textbooks have to be rewritten? I mean, think about this. Basically, a galaxy, an entire galaxy made out of a strange, invisible form of matter, and we're clueless to understand what this dark matter is. Isn't this rather revolutionary?
Well, I don't think we need to rewrite the textbooks. I mean, keep in mind, even the Milky Way is about 85% dark matter, okay? So the Milky Way itself and other galaxies are mostly dark matter, too. It's just that these ultra-diffuse galaxies push things to the extreme, being over 99% made of dark matter. So, this obviously should be in addition to any new textbook that comes out, but I don't think we need to rewrite the textbooks. I mean, all those beautiful galaxies out there, like the Milky Way, like the Whirlpool Galaxy, like the Andromeda Galaxy, they will remain as beautiful as ever. But we now have this whole new breed of galaxies to study, and hopefully they will help us understand how galaxies form and why some look one way and others look another way.
And also, we have this mental image that all these galaxies are pretty much static. They don't collide with each other. They don't morph into different kinds of galaxies. But now we realize that the universe is quite dynamic, right? Galaxies colliding with other galaxies, smashing into other galaxies. There was a notice that the dwarf galaxy Hercules is plowing into the Milky Way. So explain how dynamic these galaxies are. They're not static at all.
Not at all. Just as the planets go around the sun, there are lots of galaxies that go around the Milky Way. We know of more than 50 galaxies that orbit the Milky Way, just as moons go around a planet. One of them is the one you just mentioned, the Hercules dwarf, which is on a very elliptical orbit. It actually came closer to the galactic center than we are and is now much farther out. than we are. So all of these galaxies are very, very interesting.
Okay, well, we've run out of time. Once again, our special guest today has been our favorite astronomer, Ken Croswell of Berkeley, author of a number of great books that I highly recommend: The Alchemy of the Heavens, Magnificent Mars, Magnificent Universe, The Universe at Midnight. So check out his website, kencroswell.com.
This is Science Fantastic. Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the most amazing developments in science which touch our lives and change human destiny. Well, and once again, in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, let's move right along and take the first listener phone call.
Hi, this is Katie Jones in Chattanooga, Tennessee, Radio 1150. And my question is, I phoned it in earlier, but I didn't leave all my information. But my question is, volcanoes, why can we not utilize them as things to drop in waste, garbage, maybe nuclear waste or chemical waste? And why would that not totally disintegrate those type of things and just utilize a volcano? Thank you. Let me know.
Well, you ask a very interesting question that we physicists have actually tried to explore, but unfortunately we have pretty much given up. We've looked at the possibility of waste disposal and things like that through volcanoes, lightning, hurricanes, all sorts of natural disasters, because of course we're talking about energy on a scale that we humans cannot create. A lightning bolt can generate hundreds of millions of volts of electrical energy. But the problem with all three, with volcanoes, lightnings, and hurricanes, is that they are unstable. They're largely unpredictable. What you put in sometimes comes out again in the wrong form. So, for example, take a look at nuclear waste. If you were to put nuclear waste in a volcano, well, temporarily out of sight, out of mind, right? You think you've solved the problem. But let's say there's another eruption, and all of a sudden you have all this radioactive material being lofted in the air as fallout, raining down on the people below. Not a good idea. Or lightning bolts. Yes, it is possible. We physicists have actually sent kites up, just like Benjamin Franklin. And when a lightning bolt hits the kite, yes, electricity does go down. But again, you're talking about a very unstable form of energy. When we want energy, we want to flick the switch and be guaranteed that it's not going to blow up in our face or blow out the fuses. And hurricanes, you realize that a single hurricane has more power than 100 hydrogen bombs. Look at the size of a hurricane. Hurricanes can go hundreds of miles in extent, while a hydrogen bomb can only perhaps wipe out maybe 10 miles or maybe 30 miles. So we're talking about a very powerful force of nature in terms of lightnings, hurricanes, and volcanoes, but unfortunately they are unstable. Now, of course, if you can figure out a way to stabilize that energy, perhaps you can be recognized as the next Thomas Edison. However, at the present time, we physicists have looked into these things, but we threw up our hands and simply said, too unstable for our commercial use. Okay, well, let's move right along to the next listener phone call.
Hello, Professor Kaku. This is Steve in Scottsdale, Arizona. Actually watching your radio show on channel CRN5 on Cox Cable TV. So my question is this. I understand that obviously 4% of the entire universe's mass is made up of baryonic matter. But my question is regarding dark matter versus dark energy. It was my understanding that, or at least I thought, that dark matter really comprised of all the unseen normal matter within that baryonic percentage, i.e. black holes, brown dwarfs, things that emit very low or actually no electromagnetic radiation, or at least can't be visibly photographed or seen. So the question is, does the current calculation of 4% baryonic matter comprise all of those other traditional dark matter masses like black holes and brown dwarfs, interstellar gas, dead wandering planets, all these dark bodies? Thank you so much.
Well, the answer to your question is no. Next question. Now, let me try to answer that question by breaking it down. First of all, what is dark matter? Dark matter is invisible matter. If you held it in your hand, it would be literally invisible, but it would seep right through your fingers because it has no interaction with ordinary matter. In fact, if you held it in your hand, it would go right through the crust of the earth, through the center of the earth, all the way to China, reverse direction, and come all the way back up to New York City, and would oscillate between New York and China as if the earth did not exist, but gravity does exist. Now, we know that dark matter is real. It's not science fiction. The Hubble Space Telescope and other telescopes have given us maps of the distribution of dark matter in the universe. It is 10 times more plentiful than ordinary matter. And if you were to figure out what dark matter is, you would win the Nobel Prize in Physics. If you ever discover what dark matter is, tell me first. And maybe we'll publish together and win the Nobel Prize together. Now, let's take a short commercial break, and after the break, we'll talk about baryonic matter, and we'll talk about, well, what is this dark matter that's forcing us to revise all textbooks? Most of the universe is not made out of atoms. All the textbooks are wrong and now are being rewritten.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. It's open mic in this hour. This is the time when you can share your thoughts on national radio by giving us a call. The hotline number to call is 866-323-2129. All we ask of you is that you leave your name, call letters of the radio station, and the city you're calling from, and perhaps your thoughts can be heard on over 100 radio stations that carry Science Fantastic. Well, before the commercial break, we had a call coming in asking about dark matter and whether or not baryonic matter is within dark matter. And the short answer to that is no, but let me explain. Once again, dark matter is 10 times more plentiful than ordinary matter, but we are clueless to understand what it is really made of. At first, we thought it was dead stars, dark, invisible, things you cannot see. That's called baryonic matter. A proton is a baryon, a neutron is a baryon, atoms are baryons. So baryonic matter is a clever way of saying ordinary atoms. So we know that ordinary atoms do not make up most of dark matter. So then dark matter must be something that is not atomic. So all the high school textbooks are wrong. All the textbooks say that the world is mainly made out of atoms. Wrong. So what is the universe made of? Rather embarrassing, we don't really know for sure. Dark matter, we think, the leading candidate is that it's a higher vibration of the string. Now, realize that these strings are very tiny. It's what I do for a living, in fact, working on string theory. Each vibration corresponds to a particle. And so it turns out that these vibrating strings make up all the atoms that we see around us, but it has higher octaves, octaves that don't look like atoms at all. And so we think that dark matter is nothing but a higher octave, a higher resonance of tiny little vibrating strings. And so once again, we think that baryonic matter, that is ordinary atomic matter like you and me, we are both made out of baryonic matter, that we make up only 10%. Actually, 4% is what the caller said, depending upon how you categorize matter in the universe. But it turns out that baryonic matter only makes up a fraction of the entire universe, that dark matter makes up 10 times more, but it's invisible, and we think that it corresponds to another higher vibration of the superstring. And once again, if you want to know more about dark matter, string theory, and what I do for a living, which is string theory, get a copy of my earlier books, Hyperspace and Parallel Worlds, which have a complete description of strings, dark matter, and it answers the question, what is the universe made of anyway, if the universe is not made out of atoms? Okay, let's move right along to the next listener phone call.
Well, the name is Theodore, and I want to know what the difference is between a uranium reactor and a thorium. I've heard the thorium, when I heard Edwin Teller, I think, talk, he said they're safer. Why aren't we building them? That's my question.
Well, you ask a rather embarrassing question. First of all, Edward Teller was the father of the hydrogen bomb, and he was actually my advisor when I was in high school. When I was in high school, I built an atom smasher, and it caught his attention. I was actually playing with antimatter when I was in high school, and Edward Teller knew exactly what I was doing when I went to the National Science Fair in Albuquerque, New Mexico, and he offered me a 4-year scholarship to Harvard where I could then begin my career as a professional physicist. So I owe it all to Edward Teller. Now, you're right. If we had a chance to do it all over again, if we were back in the year 1945 or around 1950, that's when the so-called Atoms for Peace program got off the ground under President Eisenhower, and they had a choice. They had different ways of creating nuclear energy and nuclear power plants. One was thorium, and another one was uranium, cooling them with sodium, cooling them with liquid water. A variety of different kinds of reactors and fuel cycles were proposed. But then what happened was the Nautilus. Remember the Nautilus, the first atomic submarine? The Nautilus went underneath the North Pole and generated incredible headlines around the world. I mean, think about that. For the first time in human history, a submarine could go sailing right underneath the North Pole and visit the North Pole just as if there was just no inconvenience at all. Well, it fired up the imagination. Everyone said that, well, that's the future. And what was the Nautilus driven by? It was driven by uranium cooled by water. So these are called light water uranium reactors. And so we scaled up the Nautilus reactor to commercial size reactors, and that began what is now known as commercial nuclear power plants. That meant that we were wedded to a nuclear fuel cycle. The mining, milling, enrichment, waste disposal of uranium became the foundation not just of the weapons program, but also the commercial nuclear power plant program as well. Now, even back in the 50s, people were saying, well, not so fast, not so fast. Maybe we can cool the reactors with sodium. Maybe we can use a different fuel cycle based on thorium. Thorium reactors wouldn't melt so quickly. It's a whole different fuel cycle. But hey, that was 1950. In other words, it's really too late. The U.S. government and governments around the world have spent hundreds of billions of dollars perfecting the nuclear fuel cycle based on uranium, even though competing nuclear fuel cycles and competing methods could probably give uranium a run for its money. And so once again, thorium does have advantages. Thorium reactors will melt down, but they melt down much. It's more difficult for a thorium reactor to melt down, but it would take revising the entire nuclear fuel cycle on which nations have invested hundreds of billions of dollars. In other words, it's too late. It ain't going to happen. Sorry about that. Decisions made back in the 1950s with the Nautilus are with us even today. Okay, well, let's move right along to the next listener phone call.
Dr. Kaku, thank you for your show. This is Brian calling from Dallas, Texas, listening over iTunes. I'm wondering if we know that space itself is expanding rather than all matter in the universe expanding or kind of dispersing through a pre-existing space. Thank you very much.
Yes, you ask a very interesting question. Some people, when they first hear that the universe is expanding, they say to themselves, now, wait a minute. Maybe it's the atoms there that are expanding, and maybe space is not expanding at all. Or some people say, well, maybe space and matter are both expanding at the same time. So which is it? Well, first of all, if space and matter were to expand at the same rate at the same time, you would never know it, because your instruments, your eyes, everything would expand along with space, so you would never even notice the fact that the universe was expanding. However, it is space that is expanding, not matter. And how do we know that? Because if you get a telescope and you look at the distant galaxies out there, you find out that the yellow light emanating from these galaxies are redshifted. Well, we have to take a short commercial break, but after the break, I'll talk about the redshift and about how we know that it's the space between galaxies that's expanding and not the matter in the galaxies themselves.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, moving right along, let's take the next listener phone call.
Yes, I have a question regarding radio astronomy. If you're detecting a cloud of, say, carbon monoxide, 2 to 1, a pretty simple cloud, it's, say, radiating at 80 Kelvin, how is it that we're able to discern discrete frequencies from these molecules, the rotational or vibrational states? Because the cloud has got depth and you've got all these molecules that are radiating these spheres at the same time, so wouldn't you just have a signal of white noise versus a discrete frequency? The concept is a little, I guess, eludes me, and I'm not it's always eluded me, and I was just curious if you might know the answer or have an idea. Okay, thanks. Bye-bye.
Okay, well, you ask a very interesting question that actually goes to the heart of radio telescope technology and the quantum theory and nuclear magnetic resonance machines. It turns out that, yes, when you take a look at a molecule, like let's say, for example, H2O, H2O has two hydrogen atoms combined with one oxygen atom, and there are many ways to vibrate it. So think of H2O made out of Tinker Toys and combined with a spring, and then you can move the spring in different ways. You can rotate the molecule, or you can stretch it and vibrate it. Now, this is where the quantum theory comes in. It turns out that not all vibrating frequencies are possible. They are quantized. In fact, that's where the word quantum comes from. They occur in discrete packets. These are called resonances. And so, in other words, you're not going to get white noise, that is, a bunch of gibberish. White noise on a microphone sounds like this. Shh. Random white noise. You cannot distinguish individual frequencies. But you see, the vibration of the molecule is quantized. Certain resonances are not allowed. Other resonances are possible. Think of, for example, a snake that bites its tail. If the snake were to vibrate as it goes in a circle, then only certain vibrations are possible as multiples of the length of the snake. You can have vibrations that are perhaps half the length of the snake, or perhaps a third, but we're talking about integer numbers of modes that the snake can vibrate along. Not all vibrations are allowed. That's how we're able to distinguish molecules from the cloud of gibberish that we get from outer space. So let's say we're looking at a star. We're looking at a distant star. So how do you know what the star is made of? Well, you look for resonances. Atomic resonances, molecular resonances that vibrate at distinct frequencies, a fingerprint of a certain molecule. For example, when you turn on your microwave oven, have you ever noticed that things bake from the inside out rather than the outside in? When you bake a potato, you're used to having that golden crisp on the outside, because convection currents heat the outside first, and then the energy slowly goes to the inside. But in a microwave oven, it defies common sense because it heats from the inside out. And how's that? Because microwave radiation will penetrate right through the potato, and it energizes the molecular frequencies of the water vibrations. That's right, it's the water molecule that vibrates at a specific frequency that you hit with your microwave oven. So it's not white noise at all. It's a very discrete frequency that allows you to excite the water molecule, and that's how your microwave oven works.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. We're throwing the lines open because this hour is your hour. So it's open mic in this hour. So let's take the next listener phone call.
Hi, this is David. I'm calling from Meridian, Mississippi, and I was just going to ask you a question. And, well, the question is, if you were to fly around the globe and then land where you took off from, how far circumference would that be?
Well, the Earth is roughly 8,000 miles in diameter. And in high school, we realized that the circumference of a circle, you have to multiply by pi, 3.1419 ... So that means that the circumference of the Earth is 24,000 miles. Now, if the Earth is 24,000 miles in circumference, and it goes around completely in one day, that's 24 hours, that means that you are traveling at 1,000 miles an hour doing nothing. That's right. Just sitting on your rear end, you are moving at 1,000 miles per hour because it's 24,000 miles, being the circumference of the Earth, and it takes 24 hours to go 24,000 miles, and therefore you, believe it or not, are traveling at 1,000 miles an hour doing nothing. Absolutely nothing. Okay, well, let's take the next listener phone call.
Hello, Professor. My name's Mark Chubwick. I'm phoning from Southampton in the UK. I'm listening via the web. My question is, why don't robots seem to follow Moore's law and advance as fast as computers do? It just seems a little strange to me. Thanks for your time.
Well, you ask a very, very important question because, first of all, Moore's law simply states that computer power doubles every 18 months. That simple statement has energized the world economy, created social media, changed the way nations behave, and changed the way we communicate with other people. That simple statement that computer power doubles every 18 months. But artificial intelligence, that is robots, do not obey Moore's law. And therefore, we are in a situation where we expect robots to be helpers with robot maids and butlers, but we don't have them. And after the break, I'll answer the question, why don't we have robots? After all, we have everything else. Why not artificial intelligence? And maybe that's a good thing, because if we did have smart robots, perhaps they would push us out of the way, and the robots may take over. So stay tuned.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a very interesting phone question. And that is that we're so used to Moore's Law that computer power doubles every 18 months, we simply take it as our birthright that every Christmas toys are twice as powerful as they were in the previous Christmas. So, he asked, how come we don't have mechanical maids and butlers? Or for that matter, how come we don't have robots like in the Terminator? Robots that kill humans and take over the world. And so they'll put us in zoos, throw peanuts at us behind bars, and make us dance, just like we make bears dance behind bars today. What's the problem? Well, the problem is, first of all, why do we have Moore's Law? We have Moore's Law for the simple reason that we can etch tinier and tinier transistors on wafers of silicon using ultraviolet radiation. So we're very good at manipulating ultraviolet radiation. We're very good at manipulating silicon wafers. So bingo, that's the easy part. But you see, thinking does not obey Moore's Law at all. We've been spoiled into thinking that everything obeys Moore's Law. Nope. It's only the etching of transistors with ultraviolet radiation on silicon chips. That's it. Period. That's all that obeys Moore's Law, and that alone has changed world history. So we assume that everything else must obey Moore's Law. But no, cognition, thinking, reasoning, self-awareness, consciousness, all these things are extremely difficult. Now, adding machines, of course, do obey Moore's Law. That's why we have very powerful adding machines giving us the illusion that robots are thinking. Actually, they're not thinking at all. They're just very, very fast adding machines, but they don't have self-awareness. They don't have creativity. They don't have innovation because, of course, they require much more complicated algorithms than simply those found in adding machines. Now, why should you care? This is because the job market is going to be determined by this kind of technology. So why should you care? Because the future of society depends on that question. So in other words, the jobs of the future that are going to be obliterated, wiped out, literally wiped out, are repetitive jobs. Jobs that simply require bean counting, jobs that are repetitive, those jobs are going to be gone. Factory work, garment work, things that can be automated. Those jobs are going to be gone in the future. Middlemen jobs are also under pressure. That is, agency jobs, brokerage jobs, jobs involving inventory. Those jobs are going to be endangered because they involve adding machines. And that's what robots are. They're very sophisticated adding machines. So what are the jobs of the future? The jobs of the future will be jobs that involve pattern recognition. That is, recognizing voice, handwriting, faces, pattern recognition. Second, common sense. Understanding the way the world is put together, common sense. Also, interaction with humans, and also self-awareness. These four things robots cannot do at all, which means that, for example, gardeners, construction workers, policemen, they'll have jobs in the future because every construction site is different. Every garden is different. Every piece of garbage is different. Every crime is different. Those blue-collar jobs will survive in the future because they involve pattern recognition. Certain jobs that are middle class will be obliterated, like agencies. For example, brokers, stockbrokers. When you go to the stockbroker, you no longer buy stocks anymore at the stockbroker's office because you buy stocks on the internet. So why do you go to a stockbroker? Because you want intellectual capital, common sense, reasoning. You want to know who has the most experience, who's the most innovative, who knows the latest gossip, who has the best analysis. That's why you go to a stockbroker. Not to buy stocks, heaven forbid. You do that on your wristwatch. No, you go to the stockbroker because you want something that robots cannot provide, intellectual capital. So some jobs are going to be obliterated. For example, paralegals. They're going to be obliterated because paralegals mainly use search engines. And search engines, well, computers are great at search engines. But lawyers will have jobs. That's the bad news. Lawyers will have jobs in the future because lawyers have to argue to juries. They have to talk to judges. They have to understand state laws and federal laws, which change all the time, depending upon human nature and human mores. So in other words, lawyers will have jobs in the future, even though paralegals may not. And if you want to know more about this, get a copy of my book, Physics of the Future, where I list the jobs that will flourish in the future and also tell you about the jobs that are going to be wiped out as well.
This is Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we're going to throw the lines open because this is your hour. Okay, well, without further ado, let's get right to the telephones. Let's take the first listener phone call.
I received your show at WDNG 1600. I want feedback on the theory saying that the moon is only the reflection of the Earth cast into the air. We have no gravity because these are just rays. These are certainly the sun fuels off all the combustibles that are fed by the bodies on Earth. I need your feedback.
Well, I think from what you're saying, you have the idea that perhaps the moon is an illusion, that perhaps it's an illusion caused by the reflection of the Earth into outer space. I think that's what you're getting at. But let me say, first of all, that we have Newton's laws of motion, by which we can calculate precisely the forces between Mars, Jupiter, Saturn, and things like this. And that's how we send space probes. We can send a space probe right through the rings of Saturn. That's how accurate Isaac Newton's laws of motion are. And Isaac Newton's laws of motion says that the moon is real, that it does in fact revolve around the Earth, and the Earth in turn revolves around the sun. And that basic picture allows you to predict the motion of the Earth and the planets thousands, even millions of years into the future. In fact, Isaac Newton's laws of motion are some of the most precise laws that held sway for 300 years before Einstein came along and told us we have to make corrections as we go toward the speed of light. So, in other words, the basic picture that you learn in high school is actually correct. The moon, the Earth, they all have a gravitational pull, and from that you can actually calculate the mass of these objects. Or let me give you some examples. Some people say, well, how do we know how much the sun weighs or how much the Earth weighs? Well, Isaac Newton's laws of motion is a mathematical equation. In it contains the mass of the sun, the mass of the Earth, and the mass of the planets. So we can actually calculate the mass of the sun, believe it or not, even though, of course, on the Earth we can only weigh things measured in tons. Using Isaac Newton's laws of gravity, you can then calculate the mass of the sun itself. So that's incredible. That's how accurate these laws are. And it does allow us, in turn, to create a space program, to create the Internet system that can circle the entire planet, to create the GPS system. All of that complements of Isaac Newton's laws of gravity. Okay, well, moving right along, let's take the next listener phone call.
Hello, Doctor. My name is Darren. I'm from Hamilton, Montana. I listen to you on, I believe, KGVO radio in Hamilton. The question is, after listening to a question of the actual tilt of the axis of the Earth, I would like you to explain the catastrophic effect if that axis actually did change, as this lady possibly was referring to. Thank you very much for your time. I love your show.
Well, thank you. And yes, we had a previous caller on another day who was hinting about the catastrophic effects of what happens if the tilt of the Earth were to change. So let me first explain. First of all, we have not one but two kinds of north poles and south poles. We have the magnetic north and also the geologic north. Now, the magnetic north does shift. We know that for sure because we can simply look at, for example, lava flows that solidified millions of years ago. By looking, for example, at lava flows in Hawaii, as a simple example, and then simply calculating the direction of the North Pole that was frozen as the lava began to cool and eventually freeze, we begin to realize that, yes, the magnetic north has shifted dramatically over the centuries and millennia. And then the question is, what about the geologic North Pole and the geologic axis of the Earth? If that were to change, we'd be in big trouble. I mean, really big trouble. First of all, the North Pole points in the direction of Polaris. Polaris is, as any Boy Scout or Girl Scout knows, the North Star. And we know that the axis of the Earth is very stable, except for some slight perturbations. Now, these slight wobblings of the axis of the Earth can be precisely measured. And if you correlate them with other cycles of the Earth, for example, ice ages, you find a good correlation. And so it is widely believed, though we can't prove it for sure, but it's widely believed by most physicists and geologists that the reason why we had an ice age, in fact, a series of ice ages, is because of the accumulation of the tiny wobblings of the Earth. So the axis of the Earth does tilt 23 degrees with respect to the plane of the solar system, but there are tiny perturbations which in turn can be associated with ice ages. And so we do know these things happen. Now, if an ice age were to take place just on the basis of infinitesimal wanderings of the axis of the Earth, you can imagine what would happen if the Earth really tilted. In fact, I just did an interview with the History Channel, a program called The End, that is the end of the Earth, which will be broadcast perhaps in fall. And there we asked that question, what happens if a black hole were to come by and the Earth's axis were to tilt? What would happen? It would be catastrophic. First of all, the crust of the Earth would begin to break apart. We know the crustal lines where the different fault lines merge, and they would be the first to begin to break apart as the crust of the Earth began to break apart. There'd be volcanic eruptions all over the Earth if you were to change the axis of the Earth. And even the oceans, much of the oceans would be flung into outer space because of the enormous shift in the tilt of the Earth. Then the question is, has it happened in the past? And we think that it might have happened for smaller objects such as the moon. It turns out that the moon helps to stabilize the Earth's orbit. If you use Isaac Newton's laws of motion and simply run the videotape forward millions of years into the future, you can see that if the Earth had no moon, the Earth would begin to wobble. And the wobble would then begin to get larger and larger until eventually the Earth would probably flip over. Now, that would be catastrophic, of course, and we think that actually happened to perhaps Mars. Mars has two small moons, too small to stabilize the tilt and the spin of Mars. So we actually do believe that Mars actually flipped over billions of years ago. So just to summarize, if the axis of the Earth really were to shift dramatically, it would be catastrophic. The Earth would experience all sorts of catastrophic changes in the crust of the Earth with volcanoes, earthquakes, and other kinds of disruptions. And we think that it might have actually happened in the past for Mars. The Earth, luckily, has a large moon. And the effect of the gravity on the moon is to stabilize the Earth's orbit. So we can actually thank the moon for preventing this scenario, which we think actually did happen to Mars billions of years ago.
This is Science Fantastic. The most up-to-date announcements and analysis from today's technological leaders every week on Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, this is your hour. This is the time when you can get to the phones and give us a call. Okay, well, moving right along now, let's take the next listener phone call.
I'm just wondering how close we are to discovering the fourth dimension.
Well, you ask a very interesting question. In high school, we learned that the universe has 3 dimensions, length, width, and height. And anyone who talks about a fourth dimension is considered crazy, a crackpot. And there are a lot of science fiction movies and stories about people and demons and whatever that live in a higher dimension. But all these theories and speculations never got anywhere. Because, of course, the bottom line is you have to have a physics experiment to verify any of these cockamamie ideas. Well, these ideas are now taken very seriously, though we cannot yet conclusively proven. First of all, we have something called string theory, which we think is the fabled unified field theory. That is the theory of everything that allows us to explain all the different forces of the universe. String theory explains light, it explains gravity, it explains the nuclear force. And this is the theory that, in fact, eluded Einstein for the last 30 years of his life. A theory of everything. Now, you may say to yourself, well, hey, that's nice. If it really is a theory of everything, how come you guys don't win the Nobel Prize? Huh? Well, there's a problem. There's always a problem. And that is that string theory, even though it's fantastic, seems to be the theory of everything that can explain light and gravity, it has a problem, and that is it predicts that the universe was originally born in 11 dimensions. 11 dimensions, not just 4, not just 10, but 11 dimensions. And then you may say to yourself, well, that's nice, but how do you prove it? How do you prove that the universe has a higher dimension? Well, believe it or not, we can actually prove this conjecture, no matter how preposterous it may seem. First of all, we do know that gravity spreads out by the inverse square law. If you were to double your distance from the sun, for example, the strength of gravity goes down by a factor of 4. That's the inverse square law. Why is it the inverse square? Because that's the surface area of a sphere. Gravity spreads out through all space and is diluted by the fact that spheres have an area which goes as the square of the radius. So that's why we live in 3 dimensions. We can prove that we live in 3 dimensions because light and gravity spread out as the inverse square. If it's spread out as the inverse cube, the inverse quartic, the inverse quintic, then gravity would drop much faster than expected, and that's what we believe would happen if the universe had a higher dimension. So that's one way of proving it. Another way of proving it is to go back to the beginning of the universe itself. As you know, gravity waves were detected, tremendous headlines as we detected gravity waves coming from the collision of 2 black holes 1 billion light years from the planet Earth. However, the question is, even though we have evidence of gravity waves, what is the largest source of gravity waves? Well, the largest source of gravity waves, we think, is the Big Bang itself. Not just the collision of 2 black holes in outer space, but the Big Bang itself, the creation of the universe. Well, given the fact that the creation of the universe also emitted so much gravitational radiation, it should be detected by gravity wave detectors. The next generation of gravity wave detectors will be in outer space. That's right, outer space. We want to have gravity wave detectors that are so powerful they can pick up radiation from the instant of creation itself using satellites in deep space. In fact, the European Union and the United States government, NASA, both of them are planning to shoot gigantic space-based gravity wave detectors into outer space. And once we loft them into outer space, perhaps we'll have baby pictures of the instant of creation, And once we have baby pictures of the instant of creation, we'll be able to see where the universe itself came from. And string theory predicts that the universe itself came from 11-dimensional hyperspace. In fact, if you saw the movie Interstellar, starring Matthew McConaughey, it was science fiction, of course, but at the end of the movie, Matthew McConaughey is hovering above us in another dimension. And so the movie Interstellar actually ends on string theory, because string theory does predict that there are higher dimensions, in fact, other universes.
It's gravity.
Don't you get it yet, Tars? I brought myself here. We're here to communicate with the three-dimensional world. We're the bridge.
Science Fantastic with Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, this hour is your hour. This is the time when you can talk back to the radio. Okay, well, moving right along now, let's take the next listener phone call.
Wow, first of all, it's amazing to hear your voice, Dr. Kaku. I have pretty much all of your books. I was really just calling because I was curious about the show in general, what time it's at and how to listen to it and whatnot. But I don't know, here's a question for you that I haven't found the answer to, and I don't think anybody on the planet can answer, but I'm pretty sure you could, if anybody. What is energy at its rawest form? What is energy? I know it ties in with superstring theory and everything, but I'm really interested in this, and yeah, I don't know. You're the one person that I'd really like to get a response from. But yeah, I don't know if that's it. Again, it was pretty amazing to hear your voice. I have probably a book full of questions that I could ask a person like you. Like I said, I've read all your books and everything, and I'd like to make my own breakthrough someday. And yep, thanks again.
Well, thank you for the kind comments. And you want to know what energy is? Well, of course, if we did know what energy is, it would unlock some of the greatest secrets of the universe. However, in its simplest form, we define energy as simply the ability to do work. That is, the ability to move things. So energy is the quantity that allows us to move objects, okay? That's how we define energy. Mathematically speaking, is the force times the distance over which the force acts. That's the definition of energy. But the astonishing thing is that energy occurs in more than one form. In fact, it occurs in a variety of forms. First of all, we have the energy of motion, which gives us heat. Sometimes people ask, what is heat energy anyway? Heat energy is the energy of atoms in motion. That's all heat is. And then the other question is, well, what about light energy? That seems mysterious. What about gravitational energy? And how many different forms of energy are there? Well, there's light energy, there's gravitational energy, and there's nuclear energy. In fact, two types of nuclear energy, the weak force and the strong force. And as far as we can tell, that's it. There are just four fundamental forces. So what's all the problem? What is all the fuss about? The fuss is that these four forces, the force of light, gravity, and the two nuclear forces, don't like each other. They are expressed by different equations, by different physical principles. They don't seem to have anything related to each other. That is, what does light have to do with gravity having to do with the nuclear force? That's one of the greatest problems facing physics today. Well, of course, we've made progress on this question. In terms of the light, we now know that that light force can combine with some of the weak nuclear force, giving us the electroweak interaction. So the nuclear force begins to combine with the energy of light, but gravity seems to be the difficult one. In other words, a unified field theory that eluded Einstein for the last 30 years of life would unite all four all four of these forces into a single theory. Now, the leading theory for all of this is string theory. String theory unifies all of them by saying that they're nothing but different forms of music. That is, if I have A, B, C, D, they're not anything fundamental. There's nothing fundamental about C sharp or B flat. They're just musical notes on a single object, the string. So the string unifies many, many different kinds of subatomic particles, of which we have cataloged hundreds, thousands of these subatomic particles. And so now we believe that string theory can also summarize the basic forces as well. And so now we have a very simple way of explaining not just force, but matter as well. That is the theory of everything. Then you ask the question, well, where does string theory come from? Well, at that point, I'm going to have to say we don't know. We just know that the theory seems to be the theory of everything. But where did it come from? Why strings? That's what I'm working on now, trying to figure out the origin of string theory. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. This is the chance for you to get on national radio to ask that question that you've always been wanting to ask about science in this great universe of ours. Okay, well, let's move right along and take the next listener phone call.
I personally think that robots could free people with automation. What's your thoughts on the Venus Project and the guaranteed income?
Okay, well, I think you actually asked three questions. What about automatons, that is robots, and then the Venus Project, and then a guaranteed income? So let's try to break them down one by one. First of all, we've been brainwashed by Hollywood to thinking that robots are around the corner. Robots are quite primitive. They can barely recognize objects in a room. They're basically adding machines, and we forget that. So don't think that a robot is going to take your job anytime soon. But every year, we do make them smarter and smarter. Will they replace us? Maybe, but not for many a decade, perhaps late in the 21st century. Perhaps we may have robots perhaps as smart as a dog or a cat, maybe as smart as a monkey. And of course, at that point, we should put a chip in their brain to shut them off if they have murderous thoughts. And so robots do give us the possibility of saving on labor, repetitive labor. These are jobs that are dirty, dangerous, and dull, the 3 Ds. That's where robotics, I think, could have a very big impact on our economy. Jobs that are dirty, dangerous, or dull are jobs that machines can do very well. So why not let them do that? But this means that the job market will change. I mean, after all, we don't have blacksmiths anymore. We don't have wagon makers anymore, but no one cries about it either. But if you want to know what jobs are going to be phased out and what jobs are going to be opened up, then, well, get a copy of my latest book, Physics of the Future, where I have a whole chapter concerning what the future of robots is and how they will change the marketplace. Surprisingly, a whole array of new jobs will open up. But jobs that are repetitive will gradually be phased out.
Murder's a new trick for a robot. Congratulations.
What does this action signify? As you entered, when you looked at the other human, what does it mean?
It's a sign of trust. It's a human thing. You wouldn't understand.
My father tried to teach me human emotions. They are difficult.
You mean you're a designer?
Yes.
So why'd you murder him?
I did not murder Dr. Lanning.
Want to explain why you were hiding at the crime scene?
I was frightened.
Robots don't feel fear. They don't feel anything. They don't get hungry. They don't sleep.
I do. I have even had dreams.
Science Fantastic with Professor Michio Kaku. This is Science Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, and it's open mic in this hour. Well, before the break, we had a call, and he was talking not just about the future of robots, which I think is very bright. However, I don't think they're going to replace all human labor anytime soon. But he also asked a question about the Venus Project and about a guaranteed income. Well, those are pretty heavy topics, but these are basically utopian topics. The Venus Project and other projects are pushed by so-called free-thinking gurus who want to eliminate all capitalist, socialist, communist instincts and create a paradise on the earth. Well, it's been tried. In fact, the United States of America, our own backyard, was in part colonized by people from Europe who tried to create utopia. Unfortunately, it didn't quite work. All the early settlements eventually fell apart because of one basic thing: scarcity. As long as you have scarcity, you're going to have, well, people fight over these scarcities. And no matter how good the intentions are to create a utopian society, sooner or later, these scarcities catch up to you and bickering starts and people begin to fight over limited resources. But then the question is, if you fast forward it, we're not talking about America of the 1800s with the Shakers and the Quakers and other utopians. We're now talking about robots that perhaps can give us a guaranteed income. Well, at that point, all bets are off. If you look at Star Trek, for example, they have something called the replicator. You ask for it, and it comes to you. And then the question is this like a guaranteed income? Because if you want something, you simply ask for it, and the replicator creates it. So in other words, the replicator is quite a subversive instrument because it forces us to challenge all our conceptions of capitalism, socialism, and communism if you can get whatever you want by simply asking for it. Well, we physicists have tried to look into this. This is called the molecular assembler. It takes raw materials, cuts up the raw materials, and molecule for molecule creates a new form of value. So starting with nothing, all of a sudden we can have anything you want. Well, Mother Nature actually has created a molecular assembler of sorts that can cut DNA, cut proteins, and reshape them. And it's called the ribosome. A ribosome is quite miraculous. It can take hamburgers, French fries, and in 9 months, just 9 months, create a baby. Absolutely amazing. In 9 months, Mother Nature can assemble molecule for molecule the pieces you get by shattering and digesting hamburgers and French fries and creating a baby. A human baby in just 9 months. Now, then the question is, can we humans do that? And the answer is obviously no. But is it even possible? Well, there's a debate about that. You see, at the molecular level, all sorts of new quantum effects start to come in, which kind of mess up all the well-laid plans of trying to weld and splice atoms together. It is really hard to do this. It took Mother Nature billions of years to get the machinery of reproduction off the ground, and we're far away from doing that. So to answer your question, I personally don't think that the Venus Project or other utopian projects will ever succeed because we have scarcity and people will fight over scarce goods. In the future, all bets are off, but then again, in Star Trek, they live in the 23rd and 24th century. So maybe by the 23rd century, we'll have replicators, guaranteed income, and perhaps at that point, all bets are off. I should also point out that one of my favorite episodes of Star Trek, the crew of the Enterprise finds a space capsule with the bodies of people who died in the 20th century, hoping to be revived by future people so that they can cure cancer, in fact, even cure death as we know it. So the crew of the Enterprise takes in these people, they're frozen, thaws them out, and 20th century people are now living in the 23rd and 24th centuries. One of them is a banker, and he asks the crew of the Enterprise, what century is this? And when they tell him that he's now been shot hundreds of years into the future, he says to himself, my investments, my stocks, my bonds, my assets, my money. I must be rich beyond imagination. So he tells the crew to put him in contact with his stockbroker, put him in contact with his banker, because he wants to find out how much money he has. Well, the crew of the Enterprise stare at him and say, money? What is that? We don't have money. We just learn about money in history books. We have replicators. We simply ask for things, and they're given to you. Well, as you can see, this is a very subversive concept. Okay, well, moving right along, let's take the next listener phone call.
Hey, I've been watching you for years now. I love you. Good job. This is Bill. I invented a spacecraft engine, and it will do over 160,000 miles per second. It doesn't use fuel. I don't have the patent on it yet, so I can't really describe it yet, but I do have a working model. I don't think anybody believes me, but I think that it will do over the speed of light, too. You know, Einstein's theory. All right. Thank you.
Well, thanks for the generous comments. However, I would have to say that nobody has been able to go faster than the speed of light. But, hey, if you have something, patent it first before you do anything else so that no one else can steal your idea. But personally, I think, well, you may have to go back to the drawing board. So far, Einstein has been proven right every time, and he says you cannot go faster than the speed of light. Okay, sorry about that, but once again, this is Science Fantastic with Professor Michio Kaku. Tune in every week as we discuss the cutting edge of science. Good day.